All right, in this lesson, we're going to be looking at writing polynomials given either one or all of the roots. Before we cover the steps for doing that, we need to first understand the types of roots. So broadly, roots will either be real or imaginary. If you have imaginary roots, they always occur in conjugate pairs. For example, 5 plus 3i and 5 minus 3i. For real roots, the two subcategories of real numbers are rational or irrational. Rational numbers are any number that you can write as a fraction. And then irrational numbers are non-terminating and non-repeating. For example, the square root of 2. Square root of 2 is an irrational number. Pi is an irrational number. And whenever you have irrational roots, they also always occur in pairs. And then the rational roots, we can determine the number of possible rational roots using the rational root theorem. But we're going to rely on the graphs from Desmos to speed that process up to determine the rational roots. So in writing the polynomials given the roots, first thing you're going to do is write the factors from the roots. And the way that you write the factors from the roots is simply inside of parentheses x minus whatever that root is. And then once you have all the factors for each one of the roots written, you just multiply all the factors. So if we have the following roots, -1, 3, and -4, those are all rational numbers. So we just write x minus -1, which is x plus 1, x minus 3, and x minus -4, which is x plus 4. Multiply I usually multiply the factors that have the bigger numbers first. So I'm going to multiply the x minus 3 times x plus 4. X times x is x squared. And then the inner and outer terms are -3x and 4x. -3x plus 4x is x. And then -3 times 4 is -12. Now we need to distribute the x and the 1 to the x squared plus x minus 12. When we distribute the x, we get x cubed plus x squared minus 12x. When we distribute the 1, we get x squared plus x minus 12. Add up the like terms, and we get our polynomial. Now keep in mind, it's written in standard form when the coefficients are integers. They should not be fractions. The lead coefficient should be an integer, a non-negative integer. All right, so all of our coefficients are integers, so we don't have to multiply the equation by anything. All right, and our polynomial is f of x equals x cubed plus 2x squared minus 11x minus 12. Next, now we have one rational root, the -5/4, and we have one irrational root. So because we have a square root of 3 as an irrational root, we know that there's another root is also going to be negative square root of 3. So we write those two factors that correspond to those roots, x minus root 3 and x plus root 3. And then again, I'm going to multiply the factors with the radicals first. X times x is x squared, and then the inner and outer terms are going to cancel. Negative root 3x plus root 3x is just going to give us 0. And then negative root 3 times root 3 is -3. Distribute the x and the 5/4. X times x squared is x cubed. X times -3 is -3x. And notice I left a little space there because there's no x squared term whenever I distributed the x. So now when I distribute the 5/4, I get 5/4 x squared, and then 5/4 times -3 is -15 over 4. So there are no like terms to add up. So I'm just going to bring all 4 of those terms down. And then I need to write it in standard form so that in order to write it in standard form, I don't want any fractions as the coefficients. So I'm going to get rid of the fractions, I'm just going to multiply the whole equation by the lowest common denominator, which is 4. So when I multiply both sides by 4, I get f of x equals 4x cubed plus 5x squared minus 12x minus 15. And then the last example, it's an extreme circumstance. You can see here that we're given one of the roots, which is -4 plus root 7. So since the irrational numbers, they occur in conjugate pairs, we know that -4 minus root 7 is also a root. All right, there are 8 roots. Possible imaginary roots are the even numbers less than or equal to 8. So that's 0, 2, 4, and 8. 0, 2, 4, 6, and 8. The number of possible real roots is going to be 8 minus each one of the possible imaginary roots. So 8 minus 8 is 0, 8 minus 6 is 2, 8 minus 4 is 4, 8 minus 2 is 6, 8 minus 0 is 8. And then the possible rational roots are the factors of the constant at the very end over the factors of the lead coefficient, 4. Factors of 27 are plus and minus 1, 3, 9, and 27. The factors of 4 are plus and minus 1, 2, and 4. So to write out all the possible rational roots, I start with the 1, the smallest number in the numerator, biggest number in the denominator. So plus and minus 1 over 4, and then plus and minus 1 over 2, plus and minus 1 over 1. I'm going to hold off on the 1 over 1, and then I'm going to go over to the 3 over the biggest number in the denominator, which is 3/4. And then 3 over the next biggest number is 2. 3 over 2, which is 1.5. And then we've got 3 over 1, which is 3. But we're going to skip that one for just a second. And then we go to the 9. 9 over 4 is 9/4. 9 over 2. And then we're just going to hold off on the 9 over 1. And then do the same thing for the 27. 27 over 4. 27 over 2. And then now we can write all the numbers in the numerator, 1, 3, 9, and 27. All right, so those are all of our possible rational roots. So now, since we know that the irrational numbers, they occur in conjugate pairs, we know that -4 minus root 7 is another possible, another root. So I just set this equal to x, add 4 to both sides, and then I want to do the opposite of square rooting, which is squaring both sides. When I square the x plus 4, I get x squared plus 8x plus 16. And then the square root of 7 squared is just going to give me 7. It doesn't matter whether the square root is positive or negative. Anytime you square a number, it's going to end up in a positive. And then lastly, subtract 7 from both sides, and we get the depressed polynomial that contains those two roots, -4 plus and minus root 7. So we're going to take that depressed polynomial and divide it into our original polynomial. I'm just going to speed through the process. It's just long division. So when we divide that depressed polynomial x squared plus 8x plus 9 into our original polynomial, we get 4x to the 6th plus 12x to the 4th minus x squared minus 3. All right, so that is going to contain the remaining 6 roots of the original polynomial. All right, so when we take that depressed polynomial and we're going to factor it, we've got 4 terms, so we should be thinking factoring by grouping. And the first 2 terms I can factor out of 4x to the 4th, leaving me with x squared plus 3. And I would multiply the x squared by -1 to get the negative x squared. So that tells me that the -1 is the GCF for the last 2 terms. When I factor out the -1, I'm left with x squared plus 3. I've got an x squared plus 3 common to both of those terms. When I factor out the x squared plus 3, I'm left with 4x to the 4th minus 1. All right, so starting with the x squared plus 3, set that equal to 0. And we get x equals plus and minus I root 3. Those are 2 more roots. And then take the 4x to the 4th minus 1. That's the difference of 2 squares. So we can factor that. Only thing that's going to give us 4x to the 4th is 2x squared times 2x squared. Only factors of 1 is 1 and 1. 1 should be positive, 1 should be negative. And then set each one of those factors equal to 0. We get x equals plus and minus I root 2 over 2. And then when we set the 2x squared minus 1 equal to 0, we get the last 2 roots, which are plus and minus root 2 over 2.